Hello, I'm Colin Phillips.
And I'm Colin Jung.
There are many types of first-order linear differential equations. Here we will only consider first-order linear differential equations with constant coefficients. That is, we consider dp dt is equal to kp plus d, where k and d are both constants. For simplicity, in this module only, we will refer to this equation as first-order linear.
We will learn how to solve this type of differential equation and work through an example. Slide 1, Introduction. Here we consider differential equations of the form dp dt equals a constant k times p plus another constant d.
It's important to note that this and other differential equations can appear in many different forms. Consider a different looking differential equation of the form a constant a times dp dt plus a constant b times p plus a constant c is equal to 0. This differential equation looks very different, but can easily be written in the form of the first differential equation by dividing through by a and then rearranging.
We say that the first equation is in standard form. We can recognize a differential equation as first-order linear by first putting the equation in standard form. Any equation in standard form can be solved using the methods of this module. As we mentioned at the beginning of this module, we will simply call this equation first-order linear, even though that there are others.
This differential equation can be thought of as asking the question, can you find a function p which is a function of t whose derivative is equal to a constant k times this function p plus another constant d? This is a difficult question to answer just by guessing.
Slide 2, General Solution. The general solution of the first-order linear differential equation dp dt is equal to k times p plus d is
p of t is equal to an arbitrary constant a times e to the kt plus the equilibrium solution, which we will call here p subscript equilibrium, or p equilibrium.
The equilibrium solution can be found by setting the derivative in the differential equation to be 0, setting p to be equal to p equilibrium, and then solving for p equilibrium.
For our differential equation, we set dp dt equals 0 in the first equation, and we set p equal to p equilibrium. Solving this for p equilibrium, we get p equilibrium is equal to the constant negative d on k.
Notice if d was 0, our first-order linear differential equation reduces to the constant relative growth rate differential equation, and the solution to that equation is just the exponential ae to the kt. Here, when d is in general not equal to 0, we need to add in a constant, which is p equilibrium. In summary, the general solution to our first-order linear differential equation, dp dt is equal to kp plus d, consists of two parts, an exponential part and a constant part. Slide 3, Example. Let's now study an example where we want to find the general solution of a specific first-order linear differential equation. We want to find the general solution to the differential equation 2 times dp dt subtract off 6p plus 10 is equal to 0, given the condition that p of 0 is equal to 2.
These examples will be presented in a double column format, where the left-hand column corresponds to the basic theory and the right-hand column corresponds to the theory applied to our example.
Our strategy here is to first find the general solution of the differential equation. We then use the given condition to find the arbitrary constant and then the particular solution. Our first step is to rearrange the differential equation into a standard form. Here, that means we must rearrange the differential equation so that the derivative dp dt is on its own on the left-hand side.
For our example, we do this by first dividing both sides by 2. We then add 3p to both sides and subtract 5 from both sides. The equation is now in the standard form dp dt is equal to 3p minus 5. So here we want to find a function p which is a function of t such that if you differentiate it you get 3 times that function minus 5.
Step 2 is to explicitly identify the constant on the right-hand side.
For our example, k is therefore 3. So the general solution is p is equal to a e to the 3t plus p equilibrium.
So the general solution includes the equilibrium solution of the differential equation. So in step 3, we calculate the equilibrium solution. We find p equilibrium by setting the derivative dp dt equal to 0 and setting p to be p equilibrium in the differential equation.
For our example, this gives us the equation 0 is equal to 3 times p equilibrium minus 5.
We then solve for p equilibrium,
which gives p equilibrium equals 5 on 3.
In step 4, we write down our general solution. That is, what is the set of all the possible functions p, whose derivative is 3 times p minus 5.
For our example, that's the family of exponential functions p of t is equal to a e to the 3t, where a is an arbitrary constant, plus the equilibrium solution 5 on 3.
Since we want to find a particular solution, we need to identify the arbitrary constant a, using the provided condition. This is step 5. What is the given condition?
For our example, it's p of 0 is equal to 2. This means that when t equals 0, p equals 2. Graphically, this means we seek a special exponential curve that goes through the point 0, 2.
We then substitute this condition into the general solution,
which gives 2 is equal to a times e to the 3 times 0 plus the constant 5 on 3.
We then solve for a in the resulting equation,
which gives a is equal to a third. In summary, we have found that the condition p of 0 equals 2 means that a must be 1/3.
The final step is to substitute the constant into the general solution, which gives us the particular solution.
For our example, the particular solution is therefore p of t is equal to a third times e to the 3t plus the equilibrium solution 5 on 3. To summarize, we have found a particular function p, which is a function of t, that satisfies the differential equation 2 times dp dt minus 6p plus 10 is equal to 0, and the extra condition that p at 0 is equal to 2. Graphically, we have found a particular exponential curve that goes through the point 0, 2.
Slide 5. verifying our solution. To check that the answer we just obtained is a solution to the differential equation, we can simply substitute the answer into the differential equation and show that both sides are indeed equal. Here, we will substitute our solution into dp dt equals 3p minus 5. The left-hand side of the differential equation is the derivative dp dt. Now substituting our answer p of t is equal to a third times e to the 3t plus 5 on 3 into the derivative gives
d by dt of a third times e to the 3t plus 5 on 3, which is 1/3 times the derivative of e to the 3t plus the derivative of 5 on 3, which gives a third times 3 times e to the 3t from the chain rule plus 0, which simplifies to just e to the 3t after cancelling out the constants. Now the right-hand side of the differential equation is 3p minus 5. Substituting our answer in for p gives 3 times our answer a third times e to the 3t plus 5 on 3 minus 5. After expanding the brackets, this gives 3 times a third times e to the 3t plus 5 minus 5. After cancelling the 5s, we're left with 3 times a third times e to the 3t. After multiplying the 3 and the third, this simplifies to e to the 3t. This shows that the left-hand side and the right-hand side are equal, and so our answer is indeed a solution to the differential equation.
This process of substituting a possible solution into a differential equation and then showing that the left-hand side is equal to the right-hand side is very useful for verifying that a function satisfies a differential equation.
If you are ever asked to verify or check that a function satisfies a differential equation, just substitute the function into the differential equation. There is no need to derive the solution. This can save a lot of time in an exam. Now returning to our equation.
Alright, here's a more challenging exercise for you, if you're feeling game. For any first-order linear DE of the form dp dt is equal to kp plus d, verify that the general solution is p of t is equal to ae to the kt plus the constant p equilibrium. As a hint, just substitute the function into the differential equation and remember that the equilibrium is equal to negative d on k.
Slide 6. Derivation of the general solution. By using an educated guess and then verification above, we found that the general solution of the first-order linear differential equation dp dt is equal to kp plus d is p of t is equal to ae to the kt plus the equilibrium solution.
We are now going to use an alternative and more general technique called separation of variables to derive the general solution for this differential equation. Please note that this section is an optional part of this module. It is, however, a compulsory part of many courses on differential equations. It is designed to satisfy the curiosities of some of the more inquisitive students.
To derive the general solution, it is useful to first derive the equilibrium solution. We do this by setting dp dt equal to 0 and setting p equal to p equilibrium. This gives 0 is equal to k times p equilibrium plus d. Rearranging, we get P equilibrium is negative d on k. Remember this as we proceed below.
It is useful to factor out k from the right-hand side of the differential equation. We can do this by writing d as k times d on k. This gives the right-hand side of the differential equation as kp plus k times d on k. Now remembering that P equilibrium is negative d on k, we can write the right-hand side as k times P minus k times negative d on k. Remember from above that negative d on k is the equilibrium solution. To simplify the equation, we just substitute for P equilibrium. Now factoring out the k, we get dp dt equals k times all of P minus P equilibrium. The reason why we've done this is because this trick makes the differential equation a little easier to solve, and it looks simpler with the P equilibrium.
Having rewritten the original differential equation in a different form, we now use separation of variables.
For the equation dp dt equals k times P minus P equilibrium, we first note that P equals P equilibrium is a solution of the original differential equation. This is because P equilibrium is a constant, and so the derivative of P equilibrium is 0. We will use this solution later on. Now, we proceed by dividing both sides of the differential equation by P minus P equilibrium. This way we will have all the terms containing P on the left-hand side of the equation.
We next integrate both sides of the equation with respect to t. The left-hand side is equal to the integral of 1 on P minus P equilibrium times dp dt, all with respect to t.
And this is equal to the integral of 1 on P minus P equilibrium with respect to P. This step can be verified using the chain rule in reverse.
Slide 11. Simple method for remembering separation of variables. Here we give 5 simple steps to help remember the method of separation of variables shown on the last slide. They are intended as an easy method of remembering how to separate the variables in a differential equation if that is possible.
In step 1, we divide both sides by P minus P equilibrium. This gets all the terms containing P onto the left-hand side.
In step 2, we multiply both sides by dt. Even though we haven't seen how to do this without an integral sign, it is a useful tool for remembering the process. We then treat the derivative dp dt as a simple fraction and cancel out the dt's.
At this stage, we then have 1 on P minus P equilibrium times dp. And now the differential equation has all the p's on the left-hand side and all the t's on the right.
Step 3. We write an integral sign at the beginning of the left and the right-hand side, giving 2 integrals.
In step 4, we perform both these integrals. On the left-hand side, the integral of 1 on P minus P equilibrium with respect to P is the natural logarithm, or ln, of the absolute value of P minus PEQ. This can be verified by using integration by substitution.
And on the right-hand side we have the integral of k with respect to t is kt plus a constant of integration c. Even though we don't have p on its own at this stage, we do have an equation which represents the general solution.
Step 5. Rearranging the general solution for p. To get p on its own, we first raise both sides of the equation to the power of e. This gives the absolute value of p minus pq is equal to e to the kt plus c, which using an index law gives e to the kt times e to the c.
Now to remove the absolute value function on p minus pq, we use the definition of the absolute value and look at the sign of p minus pq. If p minus pq is positive, we can just remove the absolute value signs. If p minus pq is negative, we have to multiply p minus pq by -1 to make it positive.
If p minus pq is positive, then we just get p minus pq is equal to e to the c times e to the kt. On the other hand, if p minus pq is negative, then we get negative p minus pq is equal to e to the c times e to the kt.
Which implies p minus pq is equal to negative e to the c times e to the kt.
This means that we have found two solutions from removing the absolute value signs. One solution is for p minus pq negative, and one solution is for p minus pq positive. Remember earlier that we identified that p equals pq, that is, p minus pq equals 0, is also a solution to our original equations. Here, we put all of these solutions into one formula.
Case 1. If p minus peq is positive, we found that p minus peq is equal to e to the c times e to the kt. Even though c can be positive, 0 or negative, e to the c will always be positive.
Case 2 is the solution p minus pq is equal to 0. This was identified as a solution to our original equation. We can then say that p minus pq is equal to 0 times e to the kt.
Case 3. If p minus peq is negative, we found that p minus peq is equal to negative e to the c times e to the kt. We also note that negative e to the c is always negative.
We can now combine these three formulae into one equation. We can do this by calling the coefficient of e to the kt a constant a for each of these cases. For case 1, we set a is equal to e to the c, which is positive. For case 2, a equals 0, and for case 3, a equals negative e to the c, which is negative.
This gives us just one simple equation. P minus PEQ is equal to a e to the kt, where a can be positive, negative, or 0.
We then add the equilibrium solution, PEQ, to both sides to obtain the final solution, P of t equals a e to the kt plus the constant P equilibrium.